Hello, everyone. I'm Mingxi, currently the VP of Engineering at TigerGraph. This is the joint work I have conducted with Yuchen Zhang. And in this talk, I'm going to share the performance number on specific hardware on cloud, Google Cloud, and fully following the LDBC SNB BI workload at scale 10,000, roughly 10 terabytes. So as a safe harbor claim, this result is presented as it is and is ready for auditing. And it should not be used as a baseline to be compared against. So overview of what we are doing. So LDBC SNB benchmark has two workloads. And interactive is targeting OLTP, transaction and short queries. And BI workload, business intelligence, is targeting OLAP, which touch majority of the graph elements. And also it consists of multi-hop parse queries, subgraph queries, and with filtering and aggregation. And the data size is also very different. OLTP workload is usually a couple hundred at most. And BI workload target from 100 gigabytes to 36 terabytes so far. And also the update operations in the interactive workload is mostly the single point inserts. And in the BI workload, it consists of both batch inserts and the deletes. And the target metrics for the interactive is the throughput. And then the BI workload is the target metrics is mean latency for all the queries. So as I explained in the previous slides, the BI workload is targeting OLAP, and it consists of the 20 read queries, and also it generates micro batch of inserts and deletes. So TigerGraph has been using the LDBC SNB BI workload since 2018. And we start from 1 terabytes using single machine. And then 2019, we tried 4 terabytes. And then 2020, we tried 36 terabytes. And then 2022, we fully implement the driver of LDBC BI and then collaborate with LDBC. And this is the results we conducted in the past half year. And it's using TigerGraph Enterprise version 3.6 release candidate. And we use AMD CPU on Google Cloud. And the operating system is CentOS 7. And we use SSD persistent disk to store the loaded graph. And for scale, here I'm going to present two results. One is scale factor 1000, which is roughly 1 terabytes, and then scale 10,000, which is roughly 10 terabytes. For the 1000 benchmark, we use 4 AMD machine. Each one has 512 gig RAM and 2 terabytes disk. For the scale 10,000, we use 30 machines, and each machine has 768 gig RAM and 3.2 terabytes disk. So roughly for the scale 10,000, we have 23 terabytes memory in total. And here are the statistics of the graph. For scale 10,000 BI workload, the raw initial CSV dataset is 11 terabytes. And also the data generator generates the batch update data. It's also in CSV format. And the insertion file is 1.5 terabytes. And the deletion file is 24 gig. And if you look at the table on the right, the scale 1000 has 17 billion graph elements. And the scale 10,000 has 173 graph elements and consisting of 23 vertices, 23 billion vertices, and the edge is, I think, 150 billion, yeah. And TigerGraph is able to load this 10 terabytes data at the speed end-to-end into 30 machines using 1.5 hours. And breaking down the 1.5 hour on the 30 machine parallel loading, it's roughly 256 gig per hour per machine. And after loading, the 11 terabytes compressed to 6.06 terabytes in TigerGraph storage format, roughly 50% compression. And then we follow the LDBC SNB BI auditing rules, and then we do a power test. So the power test time can be broken down into 3 parts. The loading parts, which is the initial loading of the a particular snapshot. And then the insertion and deletion macro batch update, which is the writing part. And then after each writing, you do a read test of the 27 queries. So officially you have 20 queries, BI queries. And as Gabor explained in his talk, that due to the graph nature, that if your parameter touch the dense area of the graph, you may have high processing computing, high computing demands. If you touch a really sparse part of the graph, you have less computing demand. So each certain queries to break down into variations. For example, Q2A and Q2B represents different input parameter of the same query and represents expensive one, maybe in Q2A, and Q2B is a relative cheaper one. Same thing for Q8A and Q8B. They represent different input parameter, incur different computing costs. So totally considering all the variation of the query, we have 27 benchmark queries. And we report the time for scale 1,000 and 10,000 for the power run. The total power run for one batch, including the initial loading, the macro insertion, deletion, and then the read query of the 27 variations, takes 2.2 hours on 4 machine. And then for the scale 10,000, one batch of the power run take 5.8 hours total. And there are some implementation techniques that we use to speed up the read query. So we identify some pre-computation opportunities for BI 4, 6, 19, and 20. For example, for BI 4, we pre-compute for a given forum, we pre-compute the maximum member count based on the country, and then store that maximum member count as an auxiliary attribute for a forum. And then we use it for the 10 subsequent run with different parameter for that query. And the pre-computation is added to the time for the write part as part of the auditing rule. And another thing about the shortest pass. So query 15 and 19 and 20 requires you calculate shortest pass. And this shortest pass is not based on the static edge. It's based on the edge weight that you derive from the static graph. And we also break down them into two queries. The first query calculate the weights and insert those edges into the graph. And then the second query, we calculate the shortest path using the derived edges. And all this shortest path searching algorithm are implemented in GCQ. Since GCQ is Turing complete, it can express all the graph algorithm in GCQ format. So that's a little bit a correction to what Gabor presented before. So the total number of lines for GCQ, including all the shortest path implementation. So I don't think other product express graph algorithm. They use a black box calling of a Java implementation maybe. And also all the implementation of this BI query workload shared on GitHub, and you can click on the link I put in this slides. And for insertion operation, we use similar loading language. GCQ has a loading language, so we use the GCQ loading language to load all the insertion delta files. And the files are distributed on the 30-node cluster and are loaded concurrently. And the loading speed is similar to the initial snapshot loading. And the deletion, we actually do a cascading delete, and it's done by the GCQ DML queries. And in the deletion, we didn't distribute the deletion file into the 30-node cluster. Instead, we write the DML query and do a pull mode to pull all those graph elements to a single node and then delete them. Yeah. I think this concludes my talk. And we are in the process to submit this to LDBC for official auditing once we identify the right resource. Yeah. Okay.
Thanks, Mingxi, for
any
the talk.
question?
Yes, there is one from Angela.
Thank you for your talk. I was wondering what is the improvement when you apply the precomputation, because you showed the total time with the entire batch of queries. So which improvement do you obtain? Thanks.
Okay. Yeah, so the question is which improvement we identified to use the precomputation. So for the power run, the auditing rule required to run the same query 10 times. And we identify for some queries who can be decomposed into a static part and dynamic part. And then we pre-compute some statistic of the static part and store those in the graph elements. So the next 10 runs can share the pre-computation. It doesn't change the query results, but we identify the pre-computation benefits so that we can speed up the end-to-end query throughput. Yeah.
There is a question from Daniel, and then there is one in Zoom from Oscar.
Hi, thank you for the interesting talk. I was wondering, what algorithm are you using for the shortest path? I guess it's weighted shortest path in this case.
For the shortest path query, we implement a bidirectional search, BFS. So we start from two ends and then meet in the middle. And it's a parallel shortest path BFS and following the BSP model. Yeah.
How do you handle the edge weights for cheapest path? Maybe it's Bamford or Dijkstra's algorithm that seem likely.
I don't remember.
Dijkstra.
Yeah,
Dijkstra.
Dijkstra, yeah, cheapest
So
path.
it's a bidirectional Dijkstra for the ones requiring cheapest path.
Yeah.
Okay, let's.
But all the implementation we share online, so people can really check the results.
Okay, Oscar, do you have a question?
Yeah, maybe you mentioned it already, but are there like certain pre-computations that are not affected by the updates, and how exactly do you, like, do I understand correctly, like every time there's an update, you basically recompute the pre-computations?
So your question is whether the pre-computation is affected by the updates?
Yeah.
So as far as I know, the one power run includes one batch of updates, and after the batch updates, your graph engine will consume those updates, and the pre-computation happens after graph consume the updates. So you just calculate your pre-computation with incorporate updates on this new graph, and then the subsequent 10 run will just use the static part of the pre-computation.
Okay, thanks, Mingxi.
Yeah, I can also chime in here. So depending on what you choose, if you choose to run disjoint reads and writes in the throughput runs, then it's just a batch pre-computation. If you choose concurrent ones, then you do the pre-computation and then it's your responsibility to maintain it. So that of course changes the dynamics of it, and it may no longer be worth to do the pre-computation. So this is some implementation decision that we leave to the test sponsors.
Yeah,
All right,
another thing
thanks.
I want to remark based on what Neo4j slides. So it's really, I see in this graph benchmark market dynamics, people really who are serious in this benchmark work should submit their work for auditing. And in the past 1 year, so LDBC has tightened the belt. So I'm leading the brand protection for LDBC benchmark. And the concrete work we have done is in last September, we registered in UK the trademark for LDBC. And subsequently, we covered many countries all over the world with the same trademark. And it's already past the UK trademark, and the international trademark is going to be accepted very soon. So if you find any violation of LDBC brand use, you can send a complaint to LDBC, and I will work with LDBC task force to do investigation and send a legal letter to the entity who violate the rules. Okay, thank you.
One more question from Alistair.
It's always good to have a bit of controversy around here. Oscar, I'm sorry, not Oscar, Mingxi, I think that your slides ought to say on the slide which says these should not be used as a baseline for comparison, this is not an LDBC benchmark test result in line with our LDBC policies.
Yeah.
As adopted.
Yeah.
Yeah, we should be really clear about that up until the point, and it's fantastic the work you're doing and the fact you're going to get to an audit and all the rest of it. But we need to establish this principle. It's got a stamp on it. It says not an LDBC benchmark test result until it's an audited benchmark test result. That's my view. I think we need to be really, and this is a great example. Yeah, you're on the brink, but you're not there. And we need to make sure when we look at that presentation, everybody reads it, goes, that's not an LDBC test result. Whereas, as I think the colleague from Neo4j pointed out, it was really good to be able to see Galaxy Base and TigerGraph being clearly compared because they were totally comparable, because they'd gone through everything, and that was a comparable case. So we had a really good live case of being able to do what we want to be able to do in the future. Comparison between different products because they're exactly comparable tests, exactly comparable sets of results.
Yeah, that's a good point. So anything that is not officially audited, LDBC is going to give guidelines, the specific word that you should put on your work, so that people will not be confused. Okay, thank you.
Okay, well, this concludes the second session.